Hey there everyone, in this video I'm going to go over transformations of linear and absolute value functions. In the 1.2 video I did go over transformations of all types of functions, so really I'm just applying those that you learned in 1.2 to linear equations and absolute value equations. So looking at example 1, it says write a function whose graph g is a translation 3 units down of the graph f. All that means is write g of x equals, and then f of x was 2x plus 1, and then remember, by translating something up or down, you just add or subtract it to the outside. So I'll put minus 3 to the outside, and so my final answer, let's see here, what's 1 minus 3? That's negative 2. So my final answer for g of x is 2x minus 2. Okay, and so that was part A. Part B says write a function whose graph h is a translation 2 units to the left of the graph of f. So I'm going to write h of x this time, and then if you'll recall, if you want something to move left or right, you want to do it on the inside with the x. So I'll put x, and then it kind of moves opposite of what you might think. So to the left, you're going to plus 2 to the inside. So I'm going to write x plus 2, and then everything else plus 1. So everything else is the normal from before. So let's see here. I have h of x is going to equal 2x plus 4 plus 1, well, I know 4 plus 1 is 5, so my final answer on this one is 2x plus 5 for the h of x one. So example 2, you have the absolute value of x plus 3, and I meant to tack on a plus 1 right there, so it should say absolute value of x plus 3, and then plus 1 on the outside. So we're going to reflect in the x-axis for our g of x, and then our h of x will reflect in the y-axis. So reflecting in the x-axis means you have a negative on the outside. So you can write g of x equals, and you have negative x plus 3 plus 1. And it's on the outside of the whole function. So really what's happening is you have to distribute that negative to this and to that. So your g of x is officially negative x plus 3 minus 1. So it's important to note that when you're reflecting over the x, if you hadn't distributed that negative to the whole thing, you would have had a reflection. So here's the original. You would have had a reflection. I'll just crudely draw the axes right there. That would have been like right underneath it. But when you distribute the negative, you get a more proper reflection because there's like a little bit of a gap between the vertex of this. So it looks kind of like that. And the other one, if you didn't distribute that negative 1, it would be touching, they'd be like touching vertexes. But to properly reflect it, if that one's 1 up away from the x-axis, the other one needs to be 1 down away from the x-axis. So that's why you need to remember to distribute that negative. Okay? It sounds kind of confusing when I draw it because I'm terrible at drawing, but if you have a graphic calculator, just look at it that way. Okay, so the h of x for part B. Well, I'm going to reflect across the y-axis, so that is putting the negative on the inside of the function. So you have absolute value of negative x plus 3 plus 1. And that right there is kind of acceptable, but I just want to go over like what you might see, since you typically don't see stuff written like that, but sometimes you might. The equivalent of negative x plus 3 would be like extracting a negative 1, and it'd be x minus 3. Okay, and then plus 1. And so then you can write it like the absolute value of negative 1 times the absolute value of x minus 3 plus 1. And the absolute value of negative 1 is just 1. So it's just saying 1 times the absolute value of x minus 3 plus 1. And so that's just a long-winded version of saying x minus 3 plus 1 is the same thing as negative x plus 3 plus 1. So this is something I'd accept as a teacher. A student writes down on their paper, I'd accept that. But this is something that's also acceptable. And let's just say like you're taking a multiple choice test and you're looking for this. Well, think about what could be equivalent to it. Extract out that negative 1, and then the absolute value of negative 1 is 1, and so it would end up looking like this. It is a little bit confusing, I understand that, but graphically they're the same thing. All right, example 3. Let f of x be absolute value of x minus 3 minus 5. Write a function whose graph g is a horizontal shrink of the graph of f by a factor of 1/3. Okay, so here I've written down g of x, and horizontal shrink, you have to remember that it basically means it's pushing on the sides and it's getting skinnier, so it's stretching vertically. So horizontal in 1.2, I did go over that. Horizontal means it's on the inside. So I'm going to write absolute value of x minus 3 and minus 5. And so you'd be tempted to write 1/3, because the number does say 1/3. But that is not a horizontal shrink. You have to really pay close attention to the wording of this one. So 1/3 would make it get wider. And so horizontal shrink means it's going to get skinnier, right? And so horizontal means it's going to get be on the inside. And so if it's going to get skinnier, you're not going to do 1/3. You're actually going to do 3. And because it said shrink. So I don't know. That's really the best way I can explain it. This is really how the textbook words things with the horizontal shrink, stuff like that, by factor of 1/3. But if you think about it, if you just throw 1/3 in there, it's not going to shrink. It is going to get wider. So I would just encourage you to graph it and check your graph. And if it doesn't look right, just flip the fraction. 1/3 would make 3. So on part B, it'll be a little bit similar. So h of x is going to equal a vertical stretch by a factor of 2. Well, okay, so vertical stretch means it's on the outside of the function. So I'm just going to write 2, and then I can say x minus 3 minus 5. And so you might be thinking, but so why don't you do 1/2? Well, the 2 will make it stretch. So if it says vertical stretch or compression, I feel like those make sense the way they're worded, and horizontal shrink and horizontal compression kind of are like backwards. They make less sense. Yeah, again, I wish I could explain it better, but I think that's the best I can do. All right, so let's just move on to example 4. Let the graph G be a vertical shrink by a factor of 0.25 followed by a translation of 3 units up of the graph f of x equals x. Write a rule for G. Cool, so we have a combination. So I'll write G of x. So let's see here. Vertical shrink means it's going to get wider, right? So vertical shrink, if it ever says vertical, like I was saying before, just put the number, so 0.25, and then put it on the outside, x, all right? And then if you want it to go 3 units up, you just need to say plus 3. And really, that's all there is for example 4, okay? If it said something horizontal or whatever, it would be a bit more, there would be a bit more to explain, but since it says vertical, just think vertical's normal, horizontal's opposite. Okay, so write a function g whose graph is a horizontal stretch of the graph absolute value of x by a factor of 3 followed by a reflection in the y-axis. Okay, so horizontal stretch means you're pulling on it from the sides, so it's going to get wider. So I'm going to make it a 1/3 and not a 3. So you see what I mean? Like, see how it's kind of going backwards? So I'll write g of x equals, and so horizontal's on the inside, so I'll go 1/3x, and then I'll put that there. That represents the horizontal stretch right there, okay? That'll make it get wider, all right? And now we just need to reflect it in the y-axis. Well, the y-axis reflection's on the inside, so all you really need to do is just throw a negative right up front, and that'll be it. So that's the answer to example 5. So yeah, a little kind of messy with the horizontal shrink and horizontal stretch, but if you look, horizontal shrink, factor of 1/3, I used 3. So I used the whole number, I flipped it. And then this one said horizontal stretch with a factor of 3, so I used the fraction 1/3. So the horizontal stuff is kind of backwards. I just wanted to close with that. Other than that, stay tuned for more videos. Bye.